So we are based in Virginia as well. We are down in Danville, Virginia, which is ironically a good lead in, as Nancy said, to where and why we're there. I chose Danville, Virginia because of its excellent training facilities, and we are fundamentally an old machine shop that used to manufacture parts in the UK and America for the aerospace industry, particularly, and DoD. And I wanted to invest in this additive technology because I could see the huge savings in cost and lead time. So we went to Danville and we used their program to take young engineers out of and turn them into sometimes attractive or additive engineers. And that's been very successful. And that's why we've been fortunate, like Nancy, to be connected into the Centre of Excellence, which really came out of a visit we had from Admiral Capono a few years ago when he saw we were using welding to manufacture parts for Siemens Energy. And he said, well, why aren't we using this technology for making parts for the ships? Here we are now, 3 years later, with a Centre of Excellence with a machine inside it, which Nancy's provided, she showed you, along with some of the other technology we use and other powder technology. So it's been a phenomenal investment, hundreds of millions into the region for training and additive manufacturing technology investigation and expansion. For those that don't know, we're close to Greensboro and 2 hours away from Charlotte. Our current facilities is literally connected to the machining program in the cyber park in Danville. We currently employ 18 people, and our planned growth is to 50 by 25. I think the rate's going now probably be more like 100. We're already planning to move into our new state-of-the-art facility across the road, right next to the COE facility Nancy mentioned earlier. And our largest customer, it has become a DoD, I suppose, really, between the Navy and the Army, but also a lot of aerospace clients that I'll mention. We're a service provider, so we use additive technology as part of a solution to be able to print, machine, inspect, and test parts on behalf of the customer. So we're a supplier that would buy, hopefully, for example, a MELP system for some of our clients and opportunities within the DoD arena. Customers that we currently deal with, our largest was Siemens. It was the first company we started with down in Charlotte, manufacturing large gas turbine components for those guys. Nancy, we mentioned earlier, Collins, we do aerospace components for, and Northrop Space, solar power again, Rolls-Royce engine parts, and so on and so forth. And we just started moving into the space industry now as we've gained some traction and some technologies. That's something we're very proud of, and I think it's important to know a little bit about, anyone that doesn't really know much about additive, is that the federal government are behind additive manufacturing, and they created this AM2 program about a year and a half ago, and I was very lucky to be invited with the CEO of Siemens Energy to present some components that we've manufactured using our technology that we currently have. And these parts for the gas turbine engines. The aim for the initiative is all about supporting small companies like ours to work with large companies like Siemens, and they are looking at areas of requirement for the market, like qualification, which is a big headache that Nancy will know about, proving that this capability of manufacturing using this technology, also assisting small companies to be able to buy equipment, because it's multi-million-dollar investments. And the big other leg of the chair is training. There's no point in creating all this technology if no one's got the skill to actually make the parts. And in Danville, the new facility for training additive, welding, machining, and inspection of additive and other standard parts will create over 1,000 trainees just within the next year that can come and work for companies like ours and meld, and obviously the supply chain that feeds into DoD. We touched on earlier about what's the difference, and Chris did a good job of covering that, really. So what's the difference between standard ways of making stuff and our way, like additive way? And there's lots of conventional manufacturing processes that go into manufacturing a component. If we look at this picture here, you'll see all these different processes that typically you'll use to make a single part, and a conventional process, and we take that down to 3 using wire, a machine, and for actually printing and machine to maybe post-process or finish the part, if you like. And whether it's wire feed or bar stock as meld use, the principle is it's easy to buy off-the-shelf material globally, and that makes such a difference to the supply chain issues that are common all over the world now, but particularly in the US as we start to reshore, which is good news. Technologies that we use are wire-based DD. And as you know, Nancy's covered the meld sort of product in terms of printing raw materials. There are technologies out there that use powder, which we choose not to use. And that's purely on the basis that we're looking to make big parts for industry, not small parts. And this technology lends itself very well to that industry, such as meld does, as Nancy showed us earlier. So wire versus powder, why do we use wire? It's much more efficient it's 100% efficient wire. Powder, in the process using powder is sort of waste. There's a lot of ecological issues and it's expensive. It reduces contamination risk and so on and so forth. So there's challenges with powder, but at the end of the day, there's a need for that because you need small, fine, high-class parts for aerospace, et cetera, et cetera. So it's not a market that we've explored yet. How does it work? Well, in very simple terms, the customer will give us a shape or a model, as we would call it. It might be a part that they've given us that we scan. Then we'll print to that model and create a near-net shape component. Then we'll scan it, and then we'll machine the part, and it's finished. And that's our kind of like our workflow for the process we use within our business. And what you can see here, what you will see, hopefully, if the video is working okay, is an example of an aerospace planetary greenhouse. It's actually Bell helicopters, where we're printing a large aerospace component for them. Just gives you a flavour of the definition that we'll print to. And then this is where we use a laser technology, which is a lot slower, but gives much finer detail if the customer's looking for what would be a very near-net shape. So it's like close to form, where we might not need to machine it at all, or there's very little machining, so there's a big cost saving there. So it really depends on the business and the customer requirements. Let's just run through some stories really on what we've made with customers that we've worked with. This is a great example, and both of these guys have touched on this, but waste, cost and waste. You can see here, if we took that raw material block and we machined it all the way conventionally, turned it into that part on the right-hand side, there's 6 boxes of chips, as we would call them, 6 boxes of material that weigh 147 pounds, 80% waste. That's wasted. So we've actually used power, and we've used a huge machine to machine all that material away, and that's going to have to be recycled at enough cost, and a considerable cost to actually generate the part in the first place. We'll print it in the shapes, the picture from the left, and we'll machine it away, but not mass reduction in material removed. So now we're at 28% waste. We've gone from a chip weight that's 20 pounds versus 147 pounds scrap, as we would call it. That gives us the ability to reduce waste, but also reduce cost. And you can see here, the cost of this particular part saved 51% in its process overall. So there can be benefits in cost as well. But I would absolutely, Nancy, the biggest advantage of this technology is lead time, particularly in aerospace and exotic materials where you can't freely buy them. This is the last part for Siemens Energy, where we've taken the CAD and we've either used the WAM technology to wire art print it, or we've used the laser technology to print it to near-net shape. And that gives us the option to either make a part super fast or make a part a lot slower with laser, but give the customer much better definition, which is a need for some customers that require that with castings. So if you look at the process we're using here to produce that part with the art method, you can see it's a lot slower than the meld process that Nancy's shown you, but what you will be able to achieve is good definition. So it really depends on the kind of part that you require, which is why you need all these different technologies. I guess we're in the medium bracket, yeah, and Melda in the large bracket. They're like, as you can see, big as a tank. We're probably making parts that go on top of that tank, which are lighter, but not easily to machine out of a large block of material. And what you're going to see here is the same thing again, but using laser. A lot slower, but you can see there's a lot more definition. So it's a much finer finish on the part. And that allows us then to not have to machine or cut around all of the features on that part, which is a huge saving in time on a very large part like this. When you look at the part when it's finished, you can see there's a nice shiny part there, but a lot of cost into machining that. That's hundreds of hours of machining. And if we use a laser system, it becomes hundreds to 50 hours, for example. So it really depends on the application, but both technologies do lend itself well to what customers' needs. Here's where we just use the technology, laser technology, for inspection. So once we finish the part, we'll measure the part, make sure it's right size, best fit it, and that's a technology that's critical to our flow of work in our business. It's an important part of our business flow. And going back to this case study I mentioned earlier, this is a good example where we've taken a component that with a lead time that used to be nearly a year to actually buy the forging to make this part. Now, we printed that substrate, as you can see that at the top picture, in 18 hours, and we printed onto the rolled plate, which is like a plate that we've already rolled, and did it in 4.5 hours. Either way, we can print the parts so we're near that shape in a day, rather than having to wait maybe a year to actually source that material. So what the customer currently does is they stock over a year's worth of material. So there's hundreds of thousands of dollars of material sitting in a warehouse in Charlotte. They don't need any of that now. So there's a big saving in stock as well as everything else. And that's the part actually printing, if you can say that. And again, that's about 4.5 hour cycle time. And the one in the picture that's finished is actually the one that we've kept that one because the president actually's got his fingerprints on it. So we're still trying to get them off so we can use it for our own secure reasons. But it hasn't worked so far. This is just another example of a large part. I mean, it's hard to see the definition in videos sometimes. But again, it's a large stainless steel part where we're looking for definition. And that, in that particular case, the forging, which was from Germany, was taking over a year and a half. And we were manufacturing that part in about a month, totally from A to Z. I think this is an interesting component because it's a titanium part. So that is actually a part, one example part, again, that we presented to the president, that is a really cool part. It actually is part of a Rolls-Royce engine, and it flies on the Airbus A350, the new plane program. And that is actually in flight test. So when people question, so, this additive technology, does it really work? Well, there are parts now in planes that are flying, titanium parts, which are important, critical parts that are approved and flying around the world with Boeing and now Airbus as well. So it's not just a new fad or a crazy idea that might work. It's real, and it's faster. We made this part in 12 weeks. That's the whole program time. It would take over about 9 months to manufacture that part, because as Nancy said earlier, the large blocks of material, whether they're aluminum or titanium in this case, can take many, many, many months to source. Unfortunately, a lot of it comes from China as well, which doesn't help. So we'd rather buy wire within the DFAS community, which is America and European countries. It allows us to use, let's say, Western wire sources to print material rather than having to rely on Asia or Russia for the source material, which is, I think, is good news. Here's a nice little naval propeller that we've done using the laser technology. That's a stainless steel part, if anyone cares. So I think in summary, we do a mix of services. I mentioned earlier, kind of an A to Z service. And as we grow, we intend to invest in qualified equipment like MELD to offer services all over the US, as well as hopefully worldwide. But we're in it for the long term. I truly believe that this technology is here to stay, and it is now growing exponentially. So I think it's a great thing for Virginia, and I think we've got to be behind this, because we could be seen as the the pioneers in this technology, in terms of not just, I think what we've got right is we're not just doing R&D anymore. We're making parts, we're delivering parts, and we're training people now, and we're held. They're building machines that feed into the ecosystem. So we've got some really exciting things going on. And I truly believe that this project and bringing it to Virginia is a highly valued investment, and I'm right on it.
Great. Yeah, that's awesome. Thank you, Alan.